We're going to take a look at physics constraints, which is the way that we connect physics bodies together in Unreal. In other game engines, these might be called joints, but in Unreal, we have one constraint object, so it can be either a constraint actor, so a specialized kind of actor, or it can be a component that lives on another actor. And these have enough configuration that allow them to act like any constraint that you might have or any kind of joint that you might have in another game engine. And so they're quite flexible. We're using the same setup that we had previously, where we had some objects that were moving, and you might recall this from the previous scene, but I'm going to take the ground plane and I'm going to make it really large. That way, as I set things up, we'll be able to see how they're connected to everything else. So we're just going to stretch out the ground plane a little bit, and then this will give us sort of a bigger playing field to mess around with physics in. The next thing I want to do is, when we had our system set up before, we have this spinning sort of object that's hitting a cone, or missing the cone, but hitting the sphere. Instead, I'm going to constrain this first sphere to a cube. And the way I'm going to do that is by taking a cube and I'm going to place it into my scene. Then I'm going to set the cube's location so that it's centered over the sphere, because I know the sphere had a 0, 0 X and Y location on the plane. And this will then serve as the sort of anchor point for the joint that I'm going to connect to the sphere. For this example, I'm going to go ahead and just use a component. So I have this cube, and let's rename it anchor. We'll call it the anchor cube. And then I'm going to add a component to it. Let's give myself a little bit more room here. And this component, if I just type physics, we'll see physics constraint. And we can just leave it with a default name, that's fine. And what you'll notice here in the details window is that we have two actors that this joint constrains. So actor 1 and actor 2. I'm going to use a little eyedropper. This is a picker, and I'm going to just select this cube here. And that's going to be that anchor cube. And then I'm going to do it again for my other object. And I'm going to select that sphere. And now you can see that these two joints are connected. So a constraint in physics in Unreal has two connection points. And from there, you can set up multiple kinds of joints. Now you'll notice that we also have the option here. We have component name 1 and component name 2. And this allows us to connect the joints between an individual component on one actor versus another actor. This is useful when you might have multiple meshes that make up a single object, and so you might want to connect a joint to a specific part on another actor, and this is the way that you would do it. If you're connecting these two meshes to skeletal meshes, you can also specify which bones are being connected. But let's go ahead and look at the constraint behavior. In the constraints, we have several sections. Some of these are just sort of set up to deal with the simulation of physics. So enable projection. If for some reason your constraint breaks, it's going to just project your object, your actor, to the right location without having to continue trying to simulate physics. And this just helps with like visual issues that you might have. That's usually set up to by default. And then there's some other settings for there. One thing that you can select that's interesting is that you can make the parent be dominant. So you can make sure that the parent, wherever it's moved, it's going to require that the children actors that are attached by the joints are connected. And so whatever is the first object here is going to be the parent. And so you can select that to make it the dominant object if you want to do that. In terms of setting the limits, we have X, Y, and Z motion limits for our joint. If you look over here, you'll see that each one of these is locked. And what that means is that the joint is not going to allow the connected object to get any longer or stretch in any particular direction. So in the X, Y, or Z direction. If we look a little bit further down, we'll also see angular limits. And angular limits are going to determine how the constraint can move, so how this joint can move around. Right now we have swing 1 motion and swing 2 motion, and so when we get closer to the joint itself, we'll be able to see that there is a little, like some visual cues to tell us what these mean. So we'll look at these in a second. And then we have twist motion. So this lets us know if the object can twist around. Now I'm going to change out this sphere here because it's not obvious when the sphere is rotating or how it's rotating. And instead I'm going to change its mesh. Right now it is just a basic sphere, and I'm going to maybe put a cylinder on it. So let's put that cylinder on it. And then I'm going to change the material because we can't tell, because it's just like a pure white material. We can't tell if it's like spinning or anything, so I'm just going to pick something random like this brick-looking pattern, and then this will help us sort of visually determine what's happening to see if we, if things look right. So at this point we can hit play, and if we hit play, you'll see, I'm kind of close, you'll just see that the object is hanging there. So not very exciting, but we do know that the joint is working because it hasn't moved anywhere. Now, it could be that if something hit it, we would see it rotate, but we're not seeing that. So let's add some length to its position. First, I'm going to get the joint itself. So we have the anchor cube, and I'm going to select its physics constraint. And I'm going to take that physics constraint, and I'm going to move it so that it's on the bottom of this cube instead of being sort of at the top. And the reason I'm doing this is because when I get closer, you'll see, oops, my camera is moving too fast. When we get closer, what you'll see is that this sort of like outline here becomes a shape that will determine, how the joint is going to be able to move. Right now, it looks like a circle because we don't have any constraints on angular movement. So it's basically a sphere saying that this object, if it were long enough, could move anywhere or where it wants to. I'm also going to take this object and I'm going to pull it further down. And so we'll just back up a little bit here and bring it further down. And I'm just going to move this out of the way, this cone, because we don't really need it here, for example. And let's go ahead and pull it down even further. Ideally, I want it to get hit by the paddle so we can see its sort of behavior. There we go. Look at that. Looks kind of like you would expect. It's just sort of has free motion around the object. And it's getting some angular, spin to it because it's hitting it kind of at an angle. And we can sort of see they got kind of caught in there. Now what's going on is that my bottom object, remember, is a kinematic object. And so it's able to just move wherever it wants. And what that means is that the physics engine is going to have to determine how, to keep these two objects from intersecting each other when it's running. And then because the other object keeps getting its position changed, it's in essence applying some kind of force to it. And you just saw there it get a little bit confused where it kind of overlapped for a little while. And so this object so the physics engine is really determining how fast it has to accelerate every time it hits that object based on the speed of the update. Remember, all I'm doing is updating the rotation in the other object. I'm not actually applying any forces here. These objects are just interacting with each other because they're physics bodies, and based on how the object is moving frame per frame, it's forcing the other object to be pushed away from it. So that's fun and all, but let's take a look a little bit closer at this joint here so we can understand, how fast it's moving. I'm going to slow down my camera speed so I don't go zooming past everything. And I'm going to select my joint, and then I'm going to come over here to the constraints on the physics constraint. And then here we have swing one motion and swing two motion. I'm going to make these both limited. And so these are going to be limited in the 45-degree motion. This will in essence give it some cone that it can move in. So what you see here is this red cone indicates the freedom of movement that this object has. And if I play it right now, what's happened is that this object's completely come out of the constraint of this cone here. And so it's just not going to be used. It's just going to ignore it at this point. And this just happens because the physics simulation isn't going to try to put it in here automatically because it's because of the calculations that it's doing. So again, if I hit play, it's going to look pretty much like it did before. We don't see the constraints. So let's go back to this physics object now. Take a nice close look at it. What we need to do is rotate this joint so that that red cone is facing down. So I'm going to select it, and I'm going to bring up my rotate widget. There we go. And I'm going to rotate it. Oops, that is on my box. I've got to actually select my physics joint. There we go. I selected the whole thing, and that's not what I wanted to do. So let's get a little bit closer again so we can see how it's going to rotate. And then I'm going to rotate it by 90 degrees. There we go. Now it's facing downward. So the issue then is, is it going to stick within that based on, the other movement in the system? And so we can hit play, take a look at it, just to double check. And so now we'll see that it does have some movement. And again, we're seeing some errors with the physics simulation. A lot of that is because I have a kinematic object here, so that can cause some issues when you're moving objects. But generally, we can see that it's staying within the bounds that it's been given. And of course, we could make that even smaller if we wanted to, which we'll do really quick. About 20 degrees and 20 degrees. And so now you can see that it's sort of following this cone that was given to me with a 20-degree angle at the max from the cone. So let's look at a few other properties that the physics constraints allow us to set up. I have my physics constraint object selected. And I'm going to come down here to linear limits. And I'm going to set one of these to limited. And so it'll allow it to move along an axis of the joint based on some distance I put it if it's limited, so 200 units at this point. But if I look at my object, I need to see which is the correct axis. If you remember, I rotated my object. And so what I can do is take a close look at this axis. There we go. All right, and I can select the Z direction. You might assume it should be the Z direction because that's the up and down direction generally in world coordinates. But unfortunately, I've rotated my object, and so you'll notice that when I clicked on limited, I now have a green line showing me that direction that it can move, and that's definitely not the right axis, and that's because I did rotate this object, and so Z is not the correct one. So I'm going to put that back to locked, and then I can hit limited here. And this gives me, again, another axis to rotate on, and it's incorrect. I could even have two of them selected, and it's basically would give me freedom in that plane. But I don't need that. What I need these to do is be locked. And then I'm going to select this one limited, and now I can see that it in fact is this same line that the joint is connected to, that the constraint is connected to this object. So this will give me some ability for this object to move up and down in this direction. And it's by 200 units. So now if I come back and I play my game, we'll see that my object sort of drops. And it's no longer, before it was sort of like on a bar. So it was acting like it was attached and it couldn't get smaller or farther away. Now it's sort of like on a string, though it's a little bit weird because, it really only has 1 degree of freedom to move in that direction. So let's go back to the physics constraint. As you can see, when you start setting up things like this, you want to really consider, do you really need this kind of motion? Because, simulating the physics can be a little bit messy. And I'm sure you've all experienced bad physics in a game before, so you kind of want to watch out for that. One of the things I can do is I can set up soft constraints. And soft constraints will allow this object to act more like a spring instead. So coming back to my physics constraint here, and then my soft constraints, this will allow it to, basically act like a spring when it works, when it runs. And so you can see it's kind of bouncy now, sort of like a spring would be. And it just gives it some different behavior. It's really a question on, what do you want it to behave like? Do you want these soft constraints to allow it to bounce around, or do you want more solid constraints? Solid would be more like a rope, whereas, this is more like a spring instead. And then you can set the same things up for the angular motion, right? So if we come back down to the angular limits, you'll see that we have these swing limits and we have these soft constraints, which are already turned on, and we have some stiffness and some dampening and some twist limits. And so you can set all of these things up simply through the settings for this constraint. In addition to that, you'll notice that we also have the ability to add a linear motor and an angular motor. Now, linear motor is going to apply force in a particular direction. So you can think of this as like a piston, for example. It's going to push in that direction, whereas an angular motor is going to apply a twist or something to that effect, an angular momentum to the object itself. And this would be exactly for like a motor that like turns a wheel, for example. You could again set that up through here so that it constantly has a value. But again, with these, you're going to usually set them up in a way to have these access through code. So you can get a hold of the angular motor and the component part of your object in Blueprint or in C++, and then you can adjust the amount of force that's being applied and things like that, so that if you wanted to react to, say, the accelerator being pressed, then you can do that sort of setting. And if you look at the sample games that Unreal has, it has a car example, and they do a lot of this sort of stuff to make the motor actually work. The other kind of constraint you might want is something that's going to act spring-like, perhaps on a single axis. And we can do that by changing up some values on our constraint. So I'm going to select our constraint again. I'm going to go back to our angular limits, and I'm going to lock everything. So this will keep it from doing any kind of rotations that I don't want. And then I'm going to allow it to have a limited motion in the X direction. Maybe 100 units, that seems reasonable. And this is going to allow it to move up and down in the X direction. Well, I think this object's kind of low, so I'm going to bring it up here a bit. And then this will set it up so that it does that. Let me go back to my constraint again. And I'm going to turn on these soft constraints. So these soft constraints, they'll have different values if you set these up before. The soft constraint allows it to act like a spring, sort of as we've talked about before. And so I'm going to make my stiffness pretty high, so maybe like 40. This is all going to depend on the weight of the object, which is based on basically its volume of the mesh and some standard density. And so when I hit play, what we want to see is it sort of bounce like this, so that when our object rotates, our paddle, which I've turned off temporarily, starts rotating, it can hit it. And it won't be, doing too much teleportation through it. So let's set the paddle speed to 90 again. Okay, so that's a little bit too low, so we see that. So let's stop this and go back to my constraint. And we're going to go ahead and allow it to move, say, up to 150. This should give it enough movement to get all the way down. Yep, looks pretty good. And now we can go back to my paddle, and we can turn the paddle back on and reset its speed. Maybe 90. And so you can see, we sort of get this up and down movement. Of course, again, part of the problem is that we're doing some teleportation. If I changed my object out to be a sphere instead, we might get some better rotation around it. So let's do that really quick, just so you can get an idea. And we'll just select this. Then we will change this to sphere. Oops, that is a material sphere. That is not the right sphere. I want the shape sphere. There we go. And let me get my paddle turned on by default since I had turned it off. And now you'll get something that looks a little bit better, hopefully, as we bounce around, and so it's really sort of like the way something might behave if it were stuck, on a pole that could, spring up and down in essence. But whenever you set up your physics, you really want to think about how you're going to set these up so they look realistic. This is obviously all a demonstration, but it should give you an idea of the kinds of constraints you can put on your objects, how you can connect them together, and how you can make things behave properly. Now, Unreal itself has a lot of other kinds of physics. So there's physics for cloth, there's physics for, I believe, hair, there's physics for breaking objects, and all of these things can be set in other parts of the engine. The last thing you might want to look at when you're dealing with physics is the actual mesh that is used for collision detection. If you look at the notes, you'll see that there are really two ways that we deal with collision. Well, really multiple ways, but we have a broad phase collision detection, which often uses possibly axis aligned bounding boxes or something as simple as spheres, because it's easy to calculate if two spheres are intersecting. And so you will often have simplified objects on your meshes. So your meshes could be millions of polygons, millions of triangles. And you don't want to do this test between two, objects that have a million triangles each, because then you have to compare every triangle. You have to test every triangle to see if it's intersecting with another triangle. So you need to come up with a more efficient way to do this. And the easiest way is to use sort of like a broad phase collision detection, which involves a simpler mesh that is going to be used for collision detection first. And then you can either go down to more, higher level of detail if you need to. So there's many ways to do this. Unreal allows you to set up a simple and a complex mesh for your objects. So I'm going to just take this object, and there's a cylinder here. And if I double click on it, you'll see that it will bring up a mesh editor. And I'm going to just grab this and put it in my, window here. And this mesh, is a cylinder, and I can come over here to my collision object, the menu item, and I can select it, and then it'll show me what the collision object is going to be used for. Well, that's, generally pretty complex for this object. All right. And if I scroll down here, I can see in my primitives that I have a convex element and it has some members in it. And so this is basically telling me that there is some kind of object that's being used to determine if there's a collision here. Well, you'll also notice that there are other things here. I could have put a sphere around it, for example. So if I come over here to collision and I say add sphere simplified collision, then you'll see that there's now a sphere around it that can be used for collision detection. I could also, add a capsule, right? And that gives me kind of a similar shaped object. I could say add a box. And so, in essence, I can add multiple elements to this, and these will be used to test whether or not there's an actual collision. You can also individually set up your own, mesh that's going to be used. So here's the complex collision mesh. What I did is I looked at my details and I went down to collision. And the complex collision mesh is something that you would probably get from your object. So again, you would never test, fully on your own mesh. So please don't drop your own mesh in there, especially if it has a lot of polygons in it. Usually you'll use your art rendering program, your 3D modeling program, to generate a simplified mesh, and you can use that in place of it, and then it can be used. But there are obviously some complex things that might happen. For example, if you have an animated person and you wanted to be able to, roll a ball between their legs, so you're thinking of like a soccer game or something like that. Well, you need to be able to also animate this collision mesh. So there's some things to think about when you're setting this up and what and how that's going to be used. But generally, Unreal gives you great flexibility in changing up what is going to be used for that mesh. And in fact, you can set up all the settings on it by default so that it has the collision settings already set. So every time you use that mesh, it's ready to go. And so that's sort of the last bit of things that you'd like to know for just getting Unreal's physics engine to work for you in a nice way.